Hello, everybody. So today what we're going to be doing is we are going to start the process of um, embarking on the process of designing a robot from the point of view of the code. So what we're going to be doing as an example is we're going to be taking 254's 2022 robot, and we are going to start to think like, how can we actually program this robot? If you think of this robot, it's a very complex machine. So the robot does many things. It drives around the field, it intakes game pieces into the robot, and then it auto aims. It has an auto aiming functionality. So kind of the robot is always kind of in a state where it can just shoot the game piece into the target. And so it has a secondary component, which is it can actually climb at the end game. And so if you think of this robot as containing, let's say 20 different motors, I'm not sure, a bunch of different sensors, and it has to do things, it has to perform these actions in a logical way, it's very hard to actually conceptualize that. And so what we do in engineering, and in particular also, for the purpose of this discussion, for software engineering or programming, is we take a complex problem and we break it down into smaller pieces. And so we're going to be looking at a simplified view of this robot for the purpose of this call. So I have taken this robot as described by this outer rectangle, this outer box, and we call that the robot. And we can start to take the robot and chunk it up into different highly specialized subsystems, it's called. So for example, the robot's ability to drive around the field has nothing to do with the way that it intakes game elements into the robot. So we can kind of consider these as logically separate entities. And the robot, when performing kind of like a larger task, let's say such as autonomously driving to a game element and intaking it, right? The robot can just say, drivetrain, I want you to start driving. And then intake, I want you to start intaking the ball or the game element. And then it kind of goes through this series of higher level steps or higher level robot functions. And this is the way that we start to make sense of the robot and how it actually starts to come together into different subsystems and subsystems working with each other and stuff like that. So as you can see here, as a highly simplified view of any robot, let's say a robot that just shoots balls or game pieces into a target. So we can think of it as a drivetrain, an intake, kind of this indexer conveyor system, which takes the game element from the floor or from the intake into the shooter, and then into the shooter. And we are trying to get to a place where we have a framework for conceptualizing any subsystem, whether or not it is an intake, a drivetrain, a conveyor, or so on. So a drivetrain seems to be very different in function than an intake. And it definitely is, right? A drivetrain is not meant to be an intake, and an intake is not meant to be a drivetrain. But there are commonalities amongst all of these subsystems. And our goal through this process, and maybe as it will be presently described here, maybe this isn't the best way or the most complete way to logically conceptualize a generalized subsystem, but this is a good start. So what we do is when designing a subsystem is kind of this like self-contained unit. And inside of here, in programming, or in the language of Java, we are considering this to be, this is going to be implemented as a class. And a class, as we've described in a previous video or in a previous lecture, is contains two different high-level components. So the first is properties. So these are properties, and these are kind of like variables or pieces of information that the class knows about. And then there are methods. And methods, as we've described previously, let me see if I can find it. Yeah, so for example, let's say you write a class called a person class. So the properties that it can have is it can have, let's say, it can know about its weight, its height, and its age. So those are properties. And then there's logic that can be built on top of that called methods. And this is kind of like, what is their BMI? So if you know the height and weight, you can determine the BMI of a person. Okay, and in the programming world, we're going to get into that. In the subsystem world, we'll get into what these methods are. Okay, so now that we've understood that classes, let's say a subsystem, and let's start with an intake subsystem. Okay, so an intake subsystem, so what are the properties that are part of the intake? So we can further break down properties into sensors, motors, and other required variables. So internal state and stuff like that. Okay, so let's actually go to their intake. So this is, and let's figure out how an intake actually works. Okay. I don't know if I can actually draw on here, so maybe hopefully my mouse will do justice. So let's actually look at this intake and start to see how we would break this intake up into the different programming components. So this intake operates in, so the core of the intake is this sticky material, which is a roller. So the idea is that here's a motor over here. And as this motor spins, as the robot tells this motor to spin, it spins this belt right over here. And that belt is also connected over here. So you can see that as this motor is spinning, let's say counterclockwise, it's gonna roll the roller. It's gonna spin the roller in kind of in a counterclockwise motion, which if there's a game element, then this will suck in the game element. Okay, so that's the first step. So in our program, we can start to think of this intake as, well, there's a motor here, and a motor is an electrical component which we can direct in the code. So all of this right here is kind of a mechanical, and this to the code won't know about kind of these pieces of metal or these, this, all of this hardware. But what it does know is that in its world, there's a motor that can spin. Okay. And then you can see over here that there's a pneumatic piston, which what happens is it's clamped down here and up here. And what happens is when it extends outwards or inwards, it actually actuates this intake up and down. So let's read this. Let's read the description, and then we'll actually start to investigate deeper into all of these electrical systems or components. So the two intakes, remember there's an intake on the front and on the back, and that's very important. It pulls balls from the ground over the bumper and into the serializer. So there's a robot with a horizontal roller on a pneumatically actuated 4-bar to create a robust touch-it-own-it mechanism. So let's take, there's a lot of useful information right in this sentence. So there's two intakes. Okay, so that's the first thing. As we have described before, or as we have learned in a previous video, the idea, there's two concepts in object-oriented programming. There's a class, which is the blueprint. So this is a blueprint for what an intake subsystem is. And then on the other hand, there are actual instances of that. So there's going to be a front roller, a front intake. And then there's going to be a back intake. And then these intakes are both going to be, so these are what we call objects, and these are the specific subsystem. Okay. So just as in the case of over here from a previous video, let's say there's a class called a person. A class you write a single time. This is the blueprint or the definition of what a person is. But this isn't a single person, a specific person. So what you do is from this class, you create an object. You can create an Adam person, right, with certain statistics. And you can have another person called a Steve person. So they both reference this blueprint, this class, but they're different instantiations of that. Okay, so just from the, let's see, yeah. So just from the first few words, we see here the two intakes. This means that in the code, there are going to be two different objects for the subsystem. Okay, so let's continue. So these are two intakes. They pull balls from the ground, right, over the bumper and into the serializer. So from here, we'll see that the intake. Let's go back to the subsystems. Where is it? Here. That the subsystem, if we think of the subsystems kind of interfacing with each other, the intake is gonna interact with, I guess, what do they call it? A serializer. So instead of a conveyor, they call it a serializer. Okay, so we start to see how the different subsystems work together. So let's continue. Over the bumper into the serializer. Robot with horizontal rollers. Okay, on a pneumatically actuated 4-bar. Okay, so so that's what this is. And let me pull up a video. Hold on. Okay, so I just pulled up the behind the bumpers for this robot. And you can see that this intake starts within the robot frame perimeter. And what happens is you'll see...
Okay. Yeah, and so...
Hold on.
Let's intake a ball here.
You see that it can retract outwards. And as you can see over here, this is the piston. Okay, and that's this piece right here. Okay, so this right here is also kind of actuated electronically. I mean, this is powered by compressed air, but there's what we call, I believe, a solenoid, which actually says to the air, feed this way or feed this way, which will make it either go in or out. Okay, so right away we also see that from a programming point of view, this is going to be part of it. Okay, so let's continue the description, and then we'll start to do more of the decomposition. So the plates, it's 1/4 inch polycarb. Okay, so there's nothing interesting there from a programming point of view. So here is the specification for the kind of the deploy or retract mechanism. So there's cylinders, and we'll get into that. And then the rollers, so it doesn't look like there's any additional electronic or programming information. This is a specification of the type of motor, and that will be factored into the program. So essentially that's it. So from an electrical component point of view, there's two elements. There's two kind of elements. There's the motor, and then there's the piston. Okay. So what we do is we go back in here, and those are going to directly become, so those are going to be properties, two properties. So as for the properties, we're going to have a motor, and in this case it's a Falcon, Falcon 500. Okay, there's a Falcon 500 motor, and then there is a piston. So we'll get into solenoid. Let's see. So a piston. And now what we can do is start to further decompose the problem into what is this motor used for. So this motor is used to perform two different functions: intake ball or exhaust ball, right? So you can either intake the ball into your robot or exhaust the ball out of your robot. Okay, and then this solenoid here is it can do two things. It can either extend intake, or it can retract intake. Okay, and those are the two things that it can do. Let's see here. Should I go into it? For now, let's not. So basically, inside of this motor, whenever you have a motor, in the new so for example, the Falcon 500, let's actually go to, let's look at a picture. So here's a Falcon 500 motor. You'll see that this main body here is the actual motor, and over here is what we call an encoder. So how do we motivate that? Hold on. Let me think for a second. Right now we're not going to look at the encoder, because for this subsystem you don't really need it necessarily. Okay, anyway, so how does a motor work? A motor works by, if you look closely, there's two large wires here. There's a red wire and a black wire. And what happens is if you push power through let's say the red side, I mean this is highly simplified, and you put what's known as a voltage across the motor, it'll actually start spinning in a certain direction. And if you kind of reverse that current, then it'll spin in the other direction. And as you can see here, what is important for this is hold on, a power curve here. Okay. So what I want to show you is what's known as a power curve, and we're not going to get too much into it because, again, this is more for the mechanical design. But what is important is, actually, let's go back for a second. So the motor can perform two functions. It can intake or exhaust the ball. And so the first question that you can say is, so how do I actually make the motor spin? So from a high level, what you do is the motor spins according to the voltage supplied across it. So what does that mean? So if we go back over here, on the y-axis up here, you see something called current, and current is the flow of electricity through the motor. Now, as you can see, if you flow, and it's measured in what we call as amps, if you flow 0 amps through the motor, then where is it? The free speed here. So this red, we're tracking this red curve. So if you put 0 amps through the motor, you're going to get a speed of the shaft. So you'll get the motor spinning at 0 RPM. However, as you increase the amount of current that you push through the motor, let's say you push, so right here. So if you push it at 400, you'll see if you follow it down, this is the point at which 400 meets this curve. And then if you go down here, you'll see that if you push 400 amps through the, 400 watts, no. Yeah, sorry, this is a little bit embarrassing. However, so if you just follow the curve and you go down, you'll see that the motor would be spinning around 2600 RPM. So from a programming point of view, what you do is you can set the motor to be, you can push a certain amount of voltage through the motor, and it'll spin at different speeds. So by telling it what voltage you want to put across the motor, you'll get different speeds here. So that's the important part. So here you see intake or exhausting a ball is the motor will spin according to the voltage supplied across it. If you put a positive voltage across it, it'll spin, let's say, clockwise. And if you put a negative one across it, it flips the direction and it'll spin the other way. And so that's exactly how it works. So that's a motor. We will, when it becomes necessary, we will get into the encoder situation here. And the encoder is a way in order to know how fast or how much the shaft is turned. So for example, things that need precise speeds or precise distances, like when it comes to driving in a, like autonomous, you're going to need to heavily use the encoder. Or in an elevator subsystem, you'll heavily need to use the encoder for that. Okay, but for this, for the intake, it's not so necessary to say I need this wheel, the intake to be spinning at a certain kind of true computed velocity. So I'm not going to get into that for the purposes of this. So going back to this intake over here, we see that we have a piston. And now I'm going to show you FRC piston. Let's see here. Operating pneumatic cylinders. Does it have... hold on. FRC. Yeah, let's see this. Here. I think this will be a good... Yeah, so something like this, right? So what you do is on the robot, you have you have a compressor. And what it does is it takes air from the outside and it compresses it and it highly pressurizes it. So there's highly pressurized air, and you keep this in kind of like a container. And so what you do is you'll see here that there are two holes here. So this right here is one example of a cylinder with an input and an output kind of tube or hole. So what happens, right? So here, this piece right here, this is free to go in and out, in and out. It kind of like is free sliding here. But what happens is if you have air, pressurized air flowing through the system, kind of in through here and out through here, what's going to happen is it's going to force this, the, what do they call it? The rod. It's going to force it out. Okay, so it's going to be in an out position. And then if you reverse the airflow, so you, instead of the air coming in through here, if it comes in through here and out through here, it's going to force this free sliding rod in. So by switching the direction of the air, is either in or in this way and out this way, or in this way or and out this way, you'll get kind of like you'll be able to extend and retract it. And that's how pneumatics works. So, so how you do that is with what they call a solenoid. So let's see if there's like a nice picture. No. Okay. Yeah, so the hardware is called a cylinder, right? So this is the mechanical hardware to actually that actually goes in or out. But the electronic device behind it, so from the point of view of the robot, it uses what's known as a solenoid. And this is kind of like a controller, you can think of it like that, to say it's a Boolean. Should it be out? Should it be in? And there's actually like double solenoids, which can kind of have 3 phases, but that's not important. And then you have here, you'll have a compressor, which you can turn on or off. So here, a solenoid, extend or retract intake. And so what do we see here? Let's move this method out of the way. Okay. So by so what does this solenoid do? So it extends or retracts the intake, and how does it do that? You can command the solenoid to push compressed air in one direction or the other. Okay, so and in that way you can make the cylinder go in or out. Okay. Okay, so now that we understand the different sensors, I guess there's not really sensors on this, but the motors, or a better word for that is actuators, right? So an actuator is one example of an actuator is a motor. but also a solenoid or a piston that's also that is an actuator. So, and now we can take these internal properties, so we have two of them, and we can start to ask ourselves the question, what can we do with these internal actuators? Okay, and now here's where it gets interesting, because now we can ask ourselves the question, what can this intake subsystem do? And if we look back to the intake subsystem, I see it as doing effectively two different things. The first thing is it can intake a ball, it can exhaust a ball, like spit the ball out. It can extend or retract itself. Okay? So if we go back here, we can say extend intake. We can retract intake. We can intake a ball, and we can exhaust ball. And it seems like these are the four robot functions that this intake is responsible for. Okay, so now once we've okay, so once we have so the methods really are robot functions that this system is responsible for. Okay, so the methods that this subsystem should have inside of it are robot functions that the system is responsible for. This intake subsystem should know nothing about the functions of another subsystem. For example, a drivetrain. Doesn't need to know about that. It needs to know extend, retract the intake, and intake or exhaust the ball. So let's start to break down how would we extend the intake. Well, what we can do as the intake subsystem is we can look back to what are my internal properties. My internal property, for example, is I have a motor. So does the motor have anything to do with extending the intake? No, it does not. And now the solenoid, though, is responsible for extending the intake. So how would we do that? So on a very general, at a very general level, or the first level, is we can tell solenoid to direct solenoid, actuate solenoid in a direction. Again, we don't know really. I mean, it depends on which way that you put the wires in to know which way. Is it forward? Is it like a plus or is it a minus? We just don't know. Okay. So we just don't know which direction it is. So for now, I'm going to say actuate the solenoid in a given direction. Okay. And then the retract is very, very similar, but it's actuate solenoid in opposite direction. Okay. So this is essentially how we can conceptualize extending the intake. So we can actuate the solenoid in a given direction. And then this, we can retract the intake by actuating it in the other way. So there is more logic to this, which you can conceptualize, which is, let's see. If intake is already extended, don't do anything, right? Because you can add a logic, which is basically not trying to do something that you've already done, or that you're already you shouldn't try extending the intake if if you're already in an extended state. Whereas also for retracting the intake, if intake is retracted, don't do anything. So this is more like control logic that we're starting to develop into these methods. Okay. So these are the two primary methods for extending and retracting. And now the more interesting ones are intaking the ball. So when designing this intake ball method, we again look back to what are our properties. We have a motor and we have a solenoid. So intaking the ball, if you remember, is we will tell the motor to spin in a certain direction, which actually intakes the ball. Okay. So how do we intake the ball? We tell motor to spin, again, in a direction. We don't know if it's plus or minus. That we'll have to look into the documentation or maybe test it and something like that. Okay, so this is intaking the ball. We need to tell the motor to spin in a direction. And then the exhaust ball is tell motor to spin in opposite direction. Okay. So something that was brought up, which is very interesting, is that intaking a ball it's not enough to just tell the motor to spin in a given direction. Because why? What happens if you spin the motor, but this intake subsystem is stowed or is retracted? It won't actually intake the ball. So what we have to do is we are actually going to, we have to first, in the intake ball method, we have to first extend intake. So the first thing we have to do is extend the intake, and then we tell the motor to spin in a direction. So the question is, how do you extend the intake? Well, that is simply actuate solenoid in a direction, right? But what you can see here is actually code reuse going on, right? Because we've already designed this extend intake method. If you remember, it's right here. So what we can do is, instead of reinventing the wheel, we can first call extend intake method, right? Because that extend intake method will perform the required behavior to extend the intake. And then we tell the motor to spin in a given direction. Okay, so exhaust ball, that additionally is going to be first call extend intake method. And then we can tell the motor to spin in the opposite direction. So this right here is how we would conceptualize the intake subsystem. So once you've done this robot subsystem decomposition, I'm gonna just get rid of these arrows, you can take this and actually start designing the code, okay? So what we're gonna be doing is we will keep this down here, okay? And that's the intake. So the serializer, the turret, actually the shooter is a good one to do, or the elevator. I'm gonna do, so I know that we were looking at this subsystem decomposition, and we first designed the intake. I am going to skip the serializer, the turret, and shooter for now. And what I'm gonna do is I'm gonna focus on, for teaching purposes, the elevator, okay? Because there is some good, lessons that we can learn from the elevator. Okay, so just like before, right? Let's first clear out, hold on. So we're going to be focusing on the elevator subsystem now. And we are going to delete all this, okay? And also the methods. And so the idea, right, the larger idea is we want to develop for ourselves a single kind of like a repeatable way of designing any subsystem, right? An elevator, a drivetrain, whatever. And so we're going to move a little faster now that I'm kind of more in the zone and because we've already seen one example. Okay. Have my coffee and let's go. Okay, so how does an elevator work? Okay, so what is an elevator, I guess, is the first question. So let's go back to behind the bumper. Let's see.
We can eject the balls.
Oh, no, that's the
we are
shooter?
able to.
Okay.
Starting off on the climb on this side.
So you see this right over here. This is called the carriage. And let's just see how this thing works. So you see it goes
so
up
the
and
first
down.
step in our climb is we use this carriage to latch onto the middle, the level 2 bar. And from there, we are able to pull down. And as we pull down, this bar here reacts against the underside of the truss. And so if you kind of imagine it as the robot has the pivot point, that allows us to reach all the way to the traversal rung.
Okay. So, by the way, this system is very cool for hanging. It's very cool. But what you can see is this elevator, as the name implies, goes up and down. And so let's actually see in the, here, how this actually works. So again, whenever you think of motion in terms of FIRST robotics, you always think, where's the motor? Motors are how things move. So you can see that the motor for this subsystem is actually way down here. And so what happens is an elevator has a few different stages or different parts. The first is the fixed stage. So you can see that these blue bars going up here, those are fixed to the robot, okay? And then what happens is there's a series, either one or more, stages that actually perform the motion or actually move. And those are called stages, or you can think of it, another term in FIRST robotics terminology is a carriage. So this right here, this black, is actually what we call the carriage. And it's a single stage elevator, which means there's only one carriage. But you can have, if you have to reach much higher, you can actually have more than one stage. So the motor is down here, and it goes, the motor spins the shaft, and it goes through a gear reduction, and it goes here. This right here is chain, okay? So this chain is forms a closed loop all the way up here, and then it goes down. Okay, so what happens is when the motor moves, this chain either moves, in this motion, I guess clockwise or counterclockwise. And if you can see how this motor actually actuates this carriage is right over here. I believe what happens is at this point, the chain is fixed to this carriage. So what that means is that as this chain moves up, this carriage also moves up. And as the chain goes down, the carriage goes down. Okay, so that's in essence how an elevator works. So there's a single motor. Okay, so let's first read this, but to us on first glance, there's a single motor that is responsible for this entire elevator system. So the elevator and reaction arm are the first components of the inventive and fast climber. It grabs the second bar and pulls down, okay, blah, blah, blah. Okay, so the elevator. It's powered by a single Falcon 500 motor, a 41-to-1 reduction, and this is the linear speed, how fast the elevator goes up and down. So right here, we see a few things. So we see that there's a motor. Okay, so again, we go to properties and actuator, so it's a motor. So it's a motor, and this is a Falcon 500 motor. And what does it do? Responsible for raising, lowering the elevator. Okay, that is pretty simple. Okay. The single stage is moved by 25 pitch chain, which is right here. Okay, so that's as we expected. And then this, okay, blah, blah, blah. And so from as we expected, the only electrical component here that we see is the Falcon 500 motor. But now we start to encounter a few issues, right? So as we did with the intake mechanism, there was a motor. And what you do is in the intake, we said that we apply a voltage across the motor, which makes it spin. If you apply a larger voltage, it spins faster. If you apply a smaller voltage, it spins slower. But the thing is that now we actually care about the distance that the elevator is traveling. Right, so a method that we may care about, and we'll get into that, is you might care about kind of like raise elevator, okay, where you're gonna pass in maybe like traversal, and maybe that's a number, maybe that's in inches, so you want to say raise the elevator to 30 inches or something like that. If you just tell the motor you supply a voltage across it, you're not going to know how far that motor has actually made the end effector travel. So for this, we need feedback. We need feedback to tell us how far has the motor actually spun when I applied a voltage. Okay, and this is what we call, maybe I'll write it over here, open loop versus closed loop control. And so the idea behind open loop and closed loop control is open loop could say set motor at plus 12 volts. Okay, so kind of the pros of this approach is that it's simple. It's simple. But the cons of this approach, right, this is set the motor at plus 12 volts. That's a single line of code. But the cons are I don't know how far the, I guess, the elevator traveled. Okay, versus a closed looped approach, which is, I guess, closed loop approach is how would we do a closed loop approach? Like how would we tell the elevator to go 30 inches? So set motor at, I don't know, at a given voltage plus blah, blah, blah volts. Okay, then what I have to do is, I guess what I can say is while, okay, so I have to set the motor at some voltage, right? If I do it at plus 12, it's going to go super fast. If not, it's going to go slower. But then I have to check how far my elevator traveled, and if I'm not at 30 inches, keep moving motor, or keep moving the motor. If I'm at 30 inches, stop the elevator. Okay, so this right here, an elevator needs a closed loop control, right? And how do we do this? So from a property point of view, so we do not just need an actuator. A closed loop control or a feedback control is a sensor. And the sensor that is most often paired with motors, or so if a motor spins, in order to track the motor's how much it's actuated, how much it's spun, is we use what's called an encoder. Okay, and that is where we go back to this image. So over here, what's great about motors in FRC nowadays, as opposed to the times, let's say like 2012 when I was on the team, or 2009 to 2012 or something like that, 2008 to 2012, is the Falcon 500 has an encoder built into it. So you can see in the back part, there's two wires here, which, and we can get into that in a minute, is how it actually tracks how far or how many rotations this shaft has made. So I found Falcon 500, we'll need that in a second. Encoders, nice. Okay, let's actually take a minute to explain how encoders work. Okay, so the FRC documentation is great. And let's actually just read the documentation. So encoders are by far the most common method for measuring rotational motion in FRC, so i.e. measuring a motor. They produce digital signals which are less prone to noise and interference than analog devices such as potentiometers or pots. So there's three main ways encoders connect physically that are typically used in FRC. And the one we really care about is a quad encoder. Okay, so I'm wondering if we should go into, let's not go into how it actually tracks the motion, or it actually tracks the rotations. It does so by what it's called a phase difference of two pulses. But let's actually look at how we wire it up. So for a quad encoder to work, you need two wires. Maybe it's not a quadrature encoder, maybe it's a, but okay, so going back over here, this Falcon, this has two wires. Oh, does it have four? It does have four. Okay, yeah, it is a quad encoder. So there's four wires that you hook up to the robo-reel or the computer. And so what happens is yeah, fine. So let's not get into that. Yeah, let's skip that. But let's actually see how encoders work in the code. Okay, so hold on 1 second. Give me just a second, please. Okay, so an encoder measures the distance that the shaft that the motor spins. So how does it do that? What happens is the shaft goes through, so this right here is an example of one type of encoder. And this features a hole which the shaft that you want to measure goes through. Okay, and then what happens is as the shaft spins, it spins this internal like little wheel. But what happens is as this sensor, as this internal circle, as it spins, what happens is it pulses. It sends pulses every single time the internal, part of the sensor spins. So if I spin this just a little bit, let's say it'll pulse one time, which tells the sensor, okay, I have turned one pulse. And what happens is you can find in the specs saying that a complete rotation is like, 100 pulses. I think in the code usually it's 4096 pulses. Hold on. Usually it's it's a known value which you can just look up. So this encoder, as it spins, it says I've seen like 1,000 pulses, and because you know how many rotations, how many pulses equals one rotation, you'll be able to know exactly how far this thing has moved, how far it's spun. But there's an inherent issue when trying to design an elevator, and that's that encoders are very unique in that they track relative position, or relative. It doesn't know if you power on the robot when this carriage is at the top. The robot's not going to know that this carriage is at the top, right? Because it has not seen any motion, so it doesn't know that this carriage has moved at all. Versus if you power on the robot when the carriage is at the bottom, you're not going to know that, the robot is not going to know that this carriage is at the bottom. However, what will happen is after the robot has been powered on and this carriage goes down, let's say you spin the motor to make this carriage go down, from that position, it will know how many pulses have been traversed, but it doesn't know the starting location. And so that's going to be very, very important, because we need to know the absolute location of this carriage at the beginning of the match. And this is called the homing procedure, which we'll understand shortly. And then from there, then the encoder is great at knowing, okay, I've gone down 5 inches, I've gone up 30, and so on. So let's actually read this, which is a very good article. So encoders and FRC. Encoders are hardware that measure rotation. The encoder generates pulses, as we discussed earlier, that contain this information. Rotation is directly proportional to distance. One revolution of the encoder can relate to a certain amount of distance. So this ticks, these are the pulses. So the encoder ticks, or the number of pulses, times this conversion factor between how many pulses equals one rotation. I think it's like 4096 or something like that. So if you take the number of ticks, or the number of pulses, times the number of the rotations over the pulses, you do unit cancellation, and you get pure distance. And this is how an encoder works. I guess a very simple way of determining K is to read the encoder values while rotating the encoder. For example, K for a drivetrain can be found by moving the robot forward one rotation of the wheels. The distance traveled is the circumference of the wheel, and the change in ticks can be found using the console or the smart dashboard. So I guess what you could do is you can empirically determine what this K value is. Because this K value is a unit conversion from distance, as we know it, to these pulses. If you rotate the wheel by one rotation, and you measure the amount of ticks that generated, you can divide them to figure out what the conversion ratio is between distance and pulses or ticks. But I think it's also given to you. Okay, so here we get to how we actually instantiate an encoder in code. And there's a reason why I'm going through the code here, but I have not gone through the code anywhere else. So an encoder is instantiated with providing two inputs. And that corresponds to here. In the computer, you have two, for an encoder, you have two wires that you have to plug in. And so this is like, let's say port 0, and this is port 1. So inside of the code, you'll put new encoder and then 0, 1. These are the ports, the physical ports that the encoder is plugged into. Okay. And the reason why you need two is due to how it actually works. So now that we've explained this a little bit, we can maybe get into we can get into how it actually computes these pulses really quickly, and I'm not sure if this is going to be so useful. So the quad encoder measure it. Never mind. Let's just ignore it. I'm sorry. So this encoder here, you need two wires. So that's what A and B are, and there's a reverse. Okay. So what you can do is the encoder ticks can be obtained using encoder.get. So again, this right here will give you the number of pulses that have been seen from the encoder. And then you multiply it by this conversion factor and you get distance. That's how we've seen it before. When I did FRC, this was the only way to obtain distance. However, WPILib has been updated and provides distance calculations automatically. So what's really cool is you can instantiate an encoder and you can actually tell it what this K value is. And from that K value, now the encoder will do, or the encoder class will actually do this conversion automatically for you. And so it's a helper function, so you can just call encoder.getDistance, you'll get the distance. This right here is very important for the elevator. So let's read it. The use of distance for encoder readings is not actually true. Encoders read displacement, not distance. This has a couple meanings. First, encoder distance can be negative. This signals if the encoder distance was in reverse or not. Okay, fine. Okay, so this is helps to explain it. Displacement. If you walk 10 feet forward, your distance from the start is 10 feet. If you walk backwards 3 feet, your displacement is now 7 feet because the starting point is at 0. So you go from 0 to 10, but then you go back 3. So your displacement is 7. So if you were to call this distance right here, that would return 7, not 10 and then minus 3, because your starting point hasn't changed. What does this mean for your robot? The encoder can't know the height of your elevator. It can only know the distance it has raised or lowered since the robot was powered on. So if you start your lift halfway up, and your encoder will read the distance from that point instead of from the bottom of the lift, which is desired. So what you have to do is you have to do what's called a homing routine, which is you have to tell the robot to go, you have to tell the robot its starting location. And how do you do that? So the home of the lift is the bottom, is at the bottom. This is where we want the encoder to read 0, so that every single time the robot turns on, It doesn't matter if the carriage is up to begin with or down to begin with. The first thing it'll do is it'll lower the elevator until it reaches the bottom. And then once it reaches the bottom, it can tell the encoder, treat this as your 0 location, such that anything after that is all relative to a set location every single time. And so the question is, how would the code know once this elevator is at the bottom? Well, it can it can spin the motor in a certain direction to make the stage go down. But what's very important is it doesn't know once it's reached the bottom because it doesn't have a sensor for that. So that's where something called a Hall effect sensor is can be used. And a Hall effect sensor is very, very cool, and it's very useful in this situation. Okay, so what a Hall effect sensor does is it emits a pulse when there's a magnet that's nearby this sensor. Okay, so if, for example, let's say you put a little magnet on this carriage here. Okay, let's say you put it at the bottom. And you put the Hall effect sensor kind of like at the bottom at a set location. Let's say down here. Okay, so what happens is you can make the motor go down, and go slowly until your robot senses that this Hall effect sensor got a pulse, which means that a magnet is nearby. And so what you can do is once you reach the point when that pulse is detected, you know every single time that this carriage is in this exact location. And at that point, you can just call a reset to the encoder. Okay, and this zeroes out the encoder. There's one catch though, and it's extremely important. Your robot must have its lift down when the robot is turned on and when auton is started. You can, okay, fine. This is called a manual process. However, you can do what's known as an automatic homing, and that's what I just described. You can place a limit switch, or in this case, a Hall effect works great. I mean, at the bottom of the lift so that the lift triggers it when it's down. You can make a command called home lift that does the following. Yep, so it sets the lift motor to lower the lift. So you want to do it slowly because you don't want it to break the entire elevator. When the limit switch is triggered, you stop the lift motor. And then only at that point you can call encoder.reset. And this will make sure that from that point, you can know exactly where the carriage is. Okay. So with that being said here, that was a long description for how this encoder works. Okay. So the encoder is, so with that discussion being out of the way, we have two more sensors. We need an encoder, and what that's going to do is track the displacement of the carriage. Then the Hall effect, which helps with the zeroing routine. Okay. And so these are two hidden kind of properties, so sensors, that the elevator is going to need to function. Okay. So now what we're going to do is we can start to compose these methods. So, okay. So what are the methods that we care about on an elevator? So the first method that you care about is right at the beginning of the match. We want to home homing routine, right? So we want to perform a homing routine, which the point of this is to reset carriage to a known location. And that's so that when we say 30 inches, it's 30 inches from the bottom, or 30 inches, So we have not just displacement, but actual distance. So this is the homing routine. And how can we conceptualize this homing routine? Well, I mean, the first thing we have to do is move motor slowly, right? We do not want to go quickly. Or move carriage down slowly until the Hall effect sensor states, until the detects a magnet nearby. And then after that, once the sensor detects this, zero the encoder. Okay. So this is the homing routine. And then I think the only other real method that this elevator or robot function this elevator should do is raise the elevator to a certain distance. And as we said here, the pseudocode for that, or the steps for that, is we set the motor to at a certain voltage, so a certain speed. And then so check how far my elevator traveled. So check encoder. Right now we have more of a language to describe this. So check encoder distance. Check the carriage distance via encoder. Okay, so that's actually what we have to do. If I'm not at 30 inches, keep moving the motor. And if I am at 30 inches, stop the elevator. So that's essentially what we want to do here. Let's see here. Let's get into, and this is essentially the elevator subsystem. I'm wondering if, for the purposes of kind of going one step deeper, this right here is a whole topic in and of itself. And that topic is something what we call, let's see, PID. Let's see if they have some good controllers. PID control right here. Okay. Do they have pictures? If not, I'm gonna need to find pictures. FRC PID. Intro to PID. I want to see. Yeah, okay. Let's see here. How long is the video? Okay, so let's spend maybe a few minutes on this, because why not? Okay, so let's go back to this, okay? So we said that we want to raise the elevator to 30 inches. Okay, so my quote unquote logic was, and this is valid, you want to set the motor at a certain voltage. So you can say like at 12 volts to be full power, okay? Then you can check the carriage distance via the encoder. And then if I'm not at 30 inches, keep moving the motor. If I am at 30 inches, I want to stop the elevator. But this, as you can maybe see, is not so accurate. This is what we call Hold on. This is what we call a bang controller. Okay. Let's see if there's a good. The first thing is FRC related. That's funny. And yeah, I just want to find a picture. Let's see here. Okay. So basically, let's look at this picture right here. Okay, so let's say on the y-axis is position. So you can think of this as an elevator. Let's say you start at position 0, and you have what we call a set point. The set point is the distance that you want to travel. So let's say 30 inches. In this case, it's 1 meter. Okay, so what you can do is if you look at this orange graph right here, you can see that because it's so steep right here, it's going, let's say, at full speed, right? So if it's at 0 meters, it has a long way to go. So it goes full speed, and it keeps going full speed. And then what happens is at our set point of 1, it's traveling so fast already, it has a lot of inertia. So what's going to happen, even if you tell the motor stop, it's going to overshoot, right? So it's going to go above 30 inches. Okay, so it's going to go, and then it's going to have to correct itself. It's going to have to go back. Okay, and then it's going to like overshoot itself again, and then it's going to overshoot, and eventually, right, it gets better and better over time, right? Where it says, okay, I was going super fast. Now I have to be a little bit more careful. So I'm going to go slower and slower, right? So until I reach this set point. But as you can see, there are different, advantages and disadvantages of both, right? So on the one hand, if you go super fast, right, it's kind of going to be more aggressive, but it's going to get there faster, right? So, and it all depends on what you care about. And this is called the damping problem. And so you can code your system however you'd like. But one thing you can do is you can have your system under damped, which means that it'll kind of have this erratic behavior. But so that's a downside to the problem. It's going to have erratic behavior. But the pro to this approach is that you're going to get to the set point maybe a little bit faster. Whereas let's say you want to be more conservative with your approach. And you say, instead, even though I'm at 0 and I have to go to 1 meter or something like that, I don't want to be super aggressive. And so in this over-damped approach, this green arrow, remember the x-axis is time. So you can go slowly and conservatively, and eventually you will reach the set point of 30. But the downside of that, so the positive, the pro is that you're not going to overshoot the set point. But the downside is it's going to take a long time. It seems like in this over-damped case, it's taking about 5 seconds to get to 30 inches or whatever. And in this under-damped system, it gets there in like 2. And then you can tune your what's known as a control loop, and we'll get more into that a lot more later, is you can tell the behavior of the program, of the elevator, to be more erratic like this, or to be more conservative, or to be kind of quote-unquote just right, which is like an in-between, which is like a compromise between the over-damped and under-damped case. So let's just, in the next like few minutes, figure out which control scenario we want to be in for an elevator. Okay, so an elevator is something where you want to command it to go a certain distance. But the thing is that let's say you want to take it to the max height of the elevator. So if you want to take it to the max height of the elevator, imagine if the motor is going to overshoot that. The elevator is going to just break. So in some scenarios, for example, maybe with a flywheel, you don't care if it overshoots as much. But for the purpose of, oh, this is so cool. Look at that. That's cool. Nice. So for the purpose of the elevator, you do care about it overshooting and you don't want it to overshoot. So what we'll get into later, just because we were discussing this raise elevator approach, there are different control methods that we're going to consider. The one that we're going to consider also is a PID controller. Maybe you've heard of it. And then maybe in the future, we'll get into what's called a model-based controller, which actually knows some of the physics of an elevator, and from there it'll design a control system. So with that being said, to what we have discussed, let's go with this. Okay, so I guess to conclude, what we've done is we have taken two different subsystems, the intake subsystem and the elevator subsystem. We've broken them down into the properties. So properties are sensors, actuators, and other required variables. So we've looked at what the subsystem has to do. We have figured out what are the relevant properties for that. So the sensors and the actuators. And then we've asked ourselves, what does this subsystem need to take care of? What robot functions is it responsible for? It's responsible for extending the intake, retracting, intaking, or exhausting. That's the intake. And then the elevator, it has to go through a homing routine. Then it also is responsible for raising an elevator, such that now this robot subsystem decomposition, this main robot doesn't care about this individual Falcon 500, right? This robot can just tell the elevator, go up 30 inches. And then it can tell the intake, deploy and start to intake balls. So the robot can kind of like coordinate all of these subsystems together in such a way that it can perform the actual tasks that the robot needs to accomplish. Okay, so with that being said, I think this was a pretty comprehensive overview of what we've done so far with robot subsystem decomposition. So thank you very much, and we'll conclude here.